Right, so from the most modern high-tech in video, we move to Brian, who's going to give us a refresher on waves and pulses. And he's got some funny green boxes over there as well, Brian, which I think you're going to turn on, are you?
And we might let the smoke out later.
So, should be interesting. So, over to you, Brian.
Thank you very much. Well, it's often neglected, but we still use an awful lot of PAL. We might not think about it and just connect things up, but it is a signal which we use a lot. The chances are it's what you feed into your transmitter. So it is worth considering the basics. It's a big topic, so where to start? Naming the parts of the waveform is a good start. So we'll start with the sync pulses. There are two sorts, line pulses and field sync. This is the line synchronizing pulse. It's 4.7 microseconds wide and the blanking 12.05. The front porch is that little bit there between the finish of picture and the start of the sync pulse, and the back porch between the finish of the sync pulse and the start of the picture. And there are the parameters as well. We've added the colour burst now, another layer of complexity. Volts amplitude symmetrical about black level. So that's 300 millivolts there. 10 cycles plus or minus a cycle, blah-de-blah. The burst start is seconds from the leading edge of sync. You'll notice I'm sort of hovering halfway up because that is the measurement point where you measure from. And I'd like you to note that rather gentle slope. It's like that for a reason. And this is a less good one. It came off a Thomson set-top box. And you'll see there that... Oh, wrong button. The edge is much steeper and the burst is really an appalling shape. And why does this matter? Well, if the rise time there is too fast, the frequency components by the Fourier analysis are out of band, and this can lead to ringing and all sorts of other problems. And this is a really bad one I found that came out of some horrible little closed circuit TV camera. Very steep.
I notice nobody's saying anything.
Yes. Well, if this leading edge of the sync pulse is ill-defined, it can lead to an erratic trigger point in the sync separator, which can lead to jagged picture edges, or if you're feeding into an analog to digital converter, it can really play up there. Now, how to measure it? Now is a very good time to buy one of these creatures. The professional world has gone through SD and now to HD, and the second-hand market is literally awash with quality PAL measuring instruments. eBay, a £5, for heaven's sake. They cost thousands, those things did. Oh, never mind. Now, there's two sizes. There's a common half-rack one. These are all half-rack ones. They're 3U high and half a rack wide. And that one over there is 3U high and a full rack wide. And they're purpose designed. They've got all sorts of nice features. And they have a proper measurement graticule. Rather than your common and garden scope, that's actually got lines on it where the black level and the sync pulse should be. Still leaves us with inaccuracy. When you're measuring on a scope or even a professional waveform monitor, you have parallax errors, you have gain errors, you can't really trust it. And the BBC solved this in the 50s by an invention by a chap called L.E. Weaver. And in the true fashion of the BBC, they called it a Weaver box. And there, whoops, wrong button. There it is. That's a valve one. And The BBC used them, the world used them. That's a late BBC one. Tektronix and others incorporated them into their waveform monitors. Mike Cox, of the previous lecture fame, his firm built a little box that you could put in front of your scope, and it did the same job as the BBC one here. It had buttons.
I've still got the original prototype.
Yes.
Whoa.
And you can select the size of the waveform you want to measure. So there's a volt, 0.7, 0.3, and those two are the colour bar amplitudes. And can't quite read what the N one says. I'm sure it does something useful. Now it works like this. You make a precision square wave. You feed it into a three-way pad, and your video goes in there, and the output is connected to any old scope, will do. It doesn't matter about its calibration, what the gain's set to, the graticule, because what you're looking at are two superimposed waveforms which are separated by the amplitude of the square wave generator. So that gives you your precision. And what you can do is turn the gain up. Of the screen, but the bit where the two waveforms overlap is right there, and you can see with a high degree of precision the amplitude. Just going back to this one, the 1950s box, it's got a big knob there, that's calibrated in 0.1 of a dB. Can be used for the measurement, and you can have an interesting conversation with your colleague at the other end of the vid, and you can say it's low or it's high. Always very keen to pass the blame. Right, now the field synchronizing pulse is much more complex than the line synchronizing pulse. It's made out of bits and pieces. A simple cheapo camera will just have one single broad pulse and it'll cross its fingers and hope it's right. But professionally, it's made out of equalizing pulses, broad pulses, and some more equalizing pulses, and the whole thing is encompassed in field blanking. In a monochrome picture, because it's interlaced, there are odd and even fields, so you need two fields to get back to where you started from. When you add in colour, it gets more complicated. Because the phase of the burst is such that it changes from one field to the next field to the next field to the next field, you've got to go through four fields till the phase of the burst is the same as it was. Now, in the early days, this used to upset the colour decoders in the burst-locked oscillator in tellies. So Mr. Brook, the famous inventor of PAL, came up with a blanking sequence called Brook blanking, and we now have a four-field system. And by and large, that's what most engineers consider colour to be, but it's actually an eight-field system because of the subcarrier to sync phase. The subcarrier sync phase needs 8 fields to get back to where it started from. There are 709,000 odd. I was rather hoping it'd be on the next slide. Oh dear. I must apologise in some respect. I've been somewhat distracted over the last couple of weeks or so. So that's the subcarrier to sync phase relationship. I'm sure I've got some more about it further on. And this is what it looks like on the scope. There are the line sync pulses, the equalising pulses, the broad pulses, and you can see that they're actually upside down pulses in a way, and the sync separator detects those, more equalising pulses, and then back to the line synchronising pulses. The job of the equalising pulses is to stabilise the state of the signal before it arises at the sync separator. It gives a period of, for want of a better word, calm, so that each field starts at the same point when the integrator of the field sync separator is charging up. And when I was at BBC Evesham, they made us do all sorts of calculations on this, and it really does work. But modern sync separators work on a slightly different principle. They actually count the lines. So instead of waiting for a broad pulse, they know it's 625 lines, and they're counting from the last one, and they're going 311, 312, now. And I say 312 and a half because, of course, that's what your number of lines in a field. Equalising pulses, broad pulses, field blanking pulses, burst blanking pulses, these all combine to give the 4-field sequence. A key point, I wish I had 2 buttons, is that there is a negative going transition where there would be a line sync pulse. And this keeps being part of the television or A to D or whatever happy because it's got a pulse when it expects it. Now, how to measure? Well, you could use a scope, but most scopes haven't got a field separator. External sync. If you're lucky to be working from a sync pulse generator, you can feed it with line drive or field drive from your SPG, and then it will lock up wonderfully. Now, this display is pulse cross. It's a feature which is used by BT because it exposes the sync pulses. What has happened is that the scanner shifted sideways and upwards so that the bit you normally don't see is exposed. And here we have the line sync period, the burst, the front porch and the back porch, and line blanking. And dealing with the field syncs, we have got the equalising pulses there and there, the broad pulses, and there, of course, that broad pulse and on the monitor there is what it looks like. In the old days, in the valve ruled the world, SPGs were serious bits of kit. They really were. They were enormous. Doing proper division with valves is a serious business. And a monochrome SPG had 4 pulses. There was line drive, field drive, mixed blanking and mixed syncs. And these were bussed round the studio so that each piece of kit had a set of pulses and they could all run timed together. Early SPGs had 4-volt pulses, but later ones have 2-volt pulses. And these are terminated with 75 ohms in the same way as video. With the arrival of colour, there were 3 more signals to contemplate from the SPG. There was the PAL square wave, burst gate, and subcarrier. There's the subcarrier frequency. Blah-de-blah-de-blah, 0.75 of a hertz, plus or minus a hertz. And now it really was inconvenient to bus these 7 round the studio, because not only had they to work, there had to be a much higher degree of timing. So in a short space of time, Marconi produced something called a monosync, which was a sort of adding together of all the pulses in a way that they could be easily taken apart by another monosync device. But it worked, but it wasn't terribly popular, because after a short period of time, people thought that they could distribute what this signal is. Now, we call it black and burst. Obviously, it's black with a burst, or colour black. It is a picture without the picture. And it contains all the information you need to lock up your piece of equipment in a genlock mode. And of course, by now, sync pulse generators were perhaps not exactly trivial, but certainly a lot simpler than they were. We're talking about the late 60s, early 70s. And the black and burst as a reference signal was very popular. I've called the 450 millivolts peak to peak. I'm being pedantic there because that's what it is from there to there. But most people refer to it as 300 millivolts. It's either the sink or the burst is both 300 millivolts, but it's actually 450. I'm being pedantic, I'm sorry. And this reference signal was so popular that it's still in use even today with HD. It's not ideal, but most equipment in recent times have been quite happy with black and burst rather than the true reference signal which you should feed to them, which was called trisinks. Experience has shown if you're trying to lock up some character generator in a portakabin next to you, if you feed it trisinks, all appears to be wonderful, but every now and then perhaps there'll be a flash and then there'll be a shout from production and much wailing, and you give it black and burst and it doesn't flash. What's going on? Why? The PAL subcarrier can be free running. This is called non-mathematical PAL, and providing the frequency is near enough right, it will sort of work. Mathematical PAL is much more complicated, and it comes from this formula here. And one of the reasons for having mathematical PAL is to minimize the dot subcarrier pattern on the picture. As when it was first introduced, there were a great many monochrome sets, and it was considered to be a very important thing. Now, one of the things you can do with colour bars to determine if you have a proper mathematical signal is if you run your finger down here, follows. And it's a quick and easy test that you can do. That's about the right speed. And this is an SPG which I borrowed, and I'm pleased to say that it isn't mathematical PAL. Somewhere the numbers have gone wrong, because if I follow the finger up, the pattern is drifting up slowly when it should be drifting down at that speed. So that's faulty. It's not mine. Looking at the subcarrier on a waveform monitor is not terribly helpful. You can measure its amplitude, and after that you're scratching your head a bit. What you need is a vector scope, and here is a photograph of that very instrument, and there we are displaying the PAL vectors, and those dots should fall in the boxes on the graticule. Or if you wanted to measure the amplitude with some precision, you could use one of the Weaver boxes. What's up the top left? It's a very comprehensive instrument. It will do all sorts of clever things. It's got menus and memories and on-screen writing. You can just see a bit there. It won't make tea though. Now, you can see the phase of the colour vectors. The big knob there allows you to rotate them so you can measure any phase error. And the burst there is those two little deflections, and they fall on the graticule. Now, I mentioned earlier subcarrier to H phase. Now, it's very difficult to measure. So, unless you have a high-end waveform monitor, as I say, it's very difficult to measure. You don't know where you are. And those three dots there indicate the SCH phase, and they should be in that sort of quadrant where they are. If they're up there, or even worse, down there, you can expect a phone call from VT complaining about it. It was very interesting the first time I came across this. We had a very nice, expensive BBC outside broadcast vehicle, and the phone went, and VT said, "You're not locked," being helpful. So I said, what? We are locked. What's going on? And there was this sort of to and fro of banter as they wound me up. And apparently they were complaining about the SCH phase, which was a pity really, because I had nothing to measure it with. So I was faced with the embarrassing position of turning the SPG on and off till they said it was right. Funny old world, isn't it? Right, SCH phase, here we are. It will return to the same phase-to-line relationship after 8 fields, a total of 709,379 subcarrier cycles, and it's defined in EBU goodness knows what. It's hard to measure, as I've said, or impossible to measure in a middle-aged BBC outside broadcast van. The waveform monitor will also do other useful things. In this case, the vector side of it, but sometimes the waveform side can be persuaded to display a picture, which is quite useful, because, for instance, you might be wanting to use the line selector facility. The display of the picture there will have a highlighted line to show which line you've selected for close examination. And when you're bored with all that, there's always this. Now, what's that? Now, Tektronix, being an amusing sort of firm, always include, or often include, what are called Easter eggs. And my vectorscope here will play Pac-Man or Towers of Hanoi. Just talk amongst yourselves for a moment while I remember how to do it. Configure page 3, hold down version and dab that button. Do you like that? It's in a surprisingly large number of Tektronix scopes. The clever ones that have got microprocessors in them, the engineers get bored and they do things like that.
It's like their drawings, their schematics.
Yeah.
The tanks.
Yes. That's the end of that particular bit of the presentation, but I have a couple of more things that I should possibly like to show you if I can work the computing engine.
You go down to the
What, that one?
Yep. And then you are on the local disk, I think. So if you go to F, you go to the F drive.
Yes. One of the things I wanted to talk about next was the necessity to terminate correctly your video cable. Now, that's the output stage of something. It could be anything. It could be a DA, the back of a camera, or whatever. And the important things to note are that there are 75 ohm resistors in series with the output, and that point there is effectively a zero impedance point because of the feedback amplifier. So there will be 2 volts, 1 volt there when it's terminated, that's 1 volt peak to peak, 75 ohm cable through a monitor with the termination switched off and out to the next monitor, and there the termination is switched off, but it's terminated with an external 75 ohm resistor, and that works perfectly. What could go wrong? Well, what's going on here? Here's the bit of wire with the termination on the end. What's happened to that? Well, the first thing that's happened is it's got much brighter. That's because it's no longer terminated, and the 2 volts from there is effectively there because it's not the potential divider arrangement. But where's the colour gone? I haven't done anything to it. I haven't taken the colour away. All I've done is take the term off. Well, that bit of coax is a transmission line. Signal going down there that is unterminated or incorrectly terminated will be reflected back up the cable. It's like SWR on your aerial in a way. And if you're unlucky and that bit of wire is an unfortunate length, the reflection is exactly 180 degrees out for subcarrier and it cancels it out. So when you're gaily joining several televisions or a television in line with your transmitter, burst amplitude and the sync amplitude and say, oh, the burst is low, the sync amplitude is gain. Because televisions are quite clever, they do this, I've seen it happen. But your transmitter won't, so you're looking at your telly thinking it's wonderful and it's auto-adjusted its gain and the output of your transmitter's low, either in chroma or luminance. And this reflection that I mentioned, although there it's exactly cancellating the subcarrier, if that was a real picture with fine detail on it, you would see that there were reflections. If there was a transition, perhaps some railings, they would have a ghost following them. So termination is a very boring subject, but it's quite important to get it right. I was going to step on. Page down.
That's technology, Brian.
Just a series of slides. That's the burst gate off the scope from the SPG. Click. The sync pulse again. Click. Another sync pulse. This is field drive. Normally you don't see field drive outside of a particular piece of equipment because modern kit derive it from their internal SPG, and it's trivial to make now, but back in the old days it actually was distributed as a separate signal, and that's what it looks like if you were in the position to see it. Click. Similarly, line drive was distributed but now comes directly from the SPG in whatever bit of equipment it might be. Click. PAL square wave made locally. Click. And this is a test signal waveform. It's a sawtooth with subcarrier. It's not, strictly speaking, a colour signal. It hasn't got a proper colour, but what we're going to look at is the way that changes with amplitude. Click. This is the display on the vector scope, as you would see it. I've turned the vector scope gain up here, and those are the burst, and that's the subcarrier on the sawtooth in the U-axis. Click. And I had to search quite long to find an amplifier this bad. You can see there that this has plainly got differential gain. What this means is that the gain of the subcarrier changes according to the amplitude of the video. Not what you want. Hard to fix. Click. And this is what it looked like on the vector scope. It's murdered the bit of kit murdered the burst away completely, and that's what's left of the subcarrier, and you can see clearly that the phase changes. Remember, the phase is a swing this way, so not only has it got diff gain, it's got diff phase. So the result of these errors is that a viewed picture, the saturation of the colour will change according to its colour of the colour will also change according to its... You're onto a hiding to nothing. Click.
Is that the definition of NTSC?
Possibly. I think we've been round. Well, that might be it. We've seen Pac-Man. We've seen the cancellation of the subcoronal deflection. Thank you very much.
So if I turn the microphone on. Good. Right, quick pause while we load the 300 meg PowerPoint for Norman, and